Today's talk is about running multi-schedulers in Kubernetes. We will talk about how multi-schedulers are supported in Kubernetes, and also some of my team's work in this area to provide a better support for multi-schedulers. Before we start, a little bit of information about myself. My name is Xiaoning Ding. I'm from Huawei Cloud Computing Department. My team is based in Seattle area. It's in Bellevue downtown, which is pretty close to Seattle downtown, about I think about 15 miles away from this hotel. And the primary focus of my team is the core infrastructure of cloud computing, like scheduling and resource management in large-scale clusters. We use Kubernetes intensively for research and also for production purpose. And also, our team is still actively hiring. So if you are interested in this field and you are willing to move to Seattle, I would be very glad to provide more information about it after this session. So this is today's agenda. First, we will give a quick recap on how the default scheduling works in Kubernetes. In the default case, there is only one scheduler process, the default scheduler. Because we are going to talk about multiple schedulers, so it's important to first understand how a single scheduler works in the default case. Then we will talk about why we would want to run multi-schedulers. What are the scenarios and the motivations? And also, we will show how Kubernetes enables us to run multi-schedulers. After that, I will introduce the work we did to provide a better support for multi-schedulers. All this work is a part of a Huawei internal project named HaaS, Huawei Orchestration and Scheduling System. During the project, we also evaluated how multi-schedulers are supported in other systems, mainly about Mesos. It's pretty interesting to see how multi-schedulers are supported in a totally different architecture. So I will also spend several minutes to share our understanding on that, and then give a quick comparison and summary about the different architectures and its support for multi-schedulers. And after all this, I will try to leave some time for Q&A and discussion. So let's start with default scheduling. As I just mentioned, in the default case, there is only one scheduler process, the default scheduler or the native Kubernetes scheduler. Firstly, it's important to understand that in Kubernetes, pods are the atomic units for scheduling. You probably will have several user containers in one single pod, but all these containers will be scheduled onto a same node. So pods, rather than containers, are the scheduling units. Also, in the default scheduler implementation, pods are scheduled one by one. This diagram shows a typical process of pod scheduling. First, pods are submitted to an API server. They can be created by any user directly or created by some Kubernetes controllers, like daemon set controllers or some other RC controller things. Then they are persisted to etcd, and in the third step, these unscheduled pods will be picked up by the scheduler process. We know there are many pods in etcd, scheduled or unscheduled. The reason that the scheduler process can find all the unscheduled pods is that there is a field named node name in the pod spec. This field indicates which node has been assigned to run this pod. By default, it's empty, which means this pod has not been scheduled or assigned to any node. So what the scheduler process does is it keeps watching all the pods with a filtering condition that node name equals to empty. When it finds such an unscheduled pod, it will evaluate all the available nodes in the cluster, trying to find the best one for this pod. In order to do this, it will evaluate a lot of rules, which we will talk about in the next slide. Here, we only need to know that at the end of scheduling, the schedule process will identify one of the nodes as the best one for this pod. Then what it does is it will write the name of this node into the node name field. And then in the last step, step 4, all the Kubernetes agents are also watching all the pods, but they are watching with a different filtering condition. Their condition is node name equal to the name of its own node. So when the node name field is updated in step 3, this pod will be picked up automatically by the Kubernetes agent in step 4. And then the Kubernetes agent will pull the container images and to launch the pods. This is an end-to-end process of pod scheduling. In some special situations, when pods are submitted, the node name field already has a value. It means this pod has been predefined to run on a particular node. This can happen when the pods are created by some controllers, like daemon set controllers. In this case, the pods will go from step 2 to step 4 directly. It will not be scheduled because the scheduler is not even aware of this pod because it doesn't meet the filtering condition in step 3. We just mentioned that in order to find the best node for a pod, the scheduler needs to run through a lot of rules. All the rules can be divided into 2 groups in Kubernetes. The first group is a set of rules that are called predicates, which are kind of hard constraints or filters. If a node cannot meet the requirements of any predicated rule, this node will be regarded as not qualified and then filtered out. So after the scheduler evaluates all the predicates, only some of the nodes will remain there. Some of them will be filtered out. There are lots of predicated rules. Here I just list some of them. For example, the first one, pod fits resources, which means the available resource on a node should be large enough to run a pod. If the pod requires 2 gigabytes of memory, then the available memory on that node should be at least 2 gigabytes. The second rule, pod fits pod. Some pods are using host-level pod mapping, so the scheduler will make sure the corresponding pods have not been occupied on that node. Anyway, after the scheduler finishes the predicate stage, some of the nodes have been filtered out, and then the scheduler will run through the second stage, which involves the other group of rules called priorities. Each priority rule will give a score to a node candidate. This score indicates to what extent this node is preferred from the perspective of this rule. For example, here I list some most commonly used priority rules. Image locality priority. This one means if a node candidate has already downloaded the container images in its cache, then this node should receive a higher score. The second one, balanced resource allocation. The scheduler will evaluate if the resource on a node candidate to see if it's used in a balanced way, if a pod is being put on that node. Because we do not want to use up all the CPU resource on a node, but leave most of memory resource unused. Or vice versa, we use up all the memory resource, but leave most of CPU resource unused. each priority rule here is associated with a weight. So each node candidate will receive an overall score. And then scheduler simply picks the node which has the highest score. If there are more than one nodes have the same high score, in current implementation, it will pick a random one. Kubernetes is very flexible. It allows you to customize the set of rules you want to run with a concept called a scheduling policy. A scheduling policy is basically a combination of particular predicates and priorities. Currently, you can configure the scheduling policy you want in either in source code or by providing a command line parameters. In later slides, we will talk about some work we did to provide a dynamic scheduling policy. So we have discussed how a single scheduler works. Now we move to the multi-scheduler part. Probably the first question we will ask is, why we would want to run multi-schedulers? Here, by multi-scheduler, I mean multiple scheduler processes, not only multi-threads inside one process. So there are different processes, independent processes. Typically, we run multi-schedulers for the benefits of engineering flexibility, availability, and scalability. One of the main scenarios is, nowadays, it's pretty common to run different types of workloads on a single shared cluster, like long-running services, user-facing services, batch jobs, streaming jobs, all these things. So they can share resources dynamically, and we can achieve a higher resource utilization. But the different types of workloads have different scheduling requirements. For example, for a long-running service like a web server, we probably want to find a best node and the most stable node for it. Because once it's deployed, it probably will run for months or even for years. So we are willing to spend a little bit more time on scheduling itself, but we want to find the most stable nodes. But for some short jobs, that probably will only run for several minutes or even for several seconds. For those jobs, scheduling latency probably is the most important thing. And for some big data jobs, the data locality is the most important thing. Of course, we can combine different scheduling algorithms, different requirements into one scheduler. But from engineering perspective, it will be a little difficult for us to develop and maintain such a big, giant, monolithic scheduler. If we split them into several different small schedulers, each focus on a particular type of workload, it will be more flexible for us to try out different scheduler implementations, and it will also be easier for us to develop, maintain, and evolve those schedulers. This is about the flexibility. The second motivation of running multi-schedulers is about availability and scalability. If your cluster only supports one scheduler instance, and you want to update that scheduler instance, then there will be some downtime. During that period of time, pods will not be scheduled. But if your cluster supports multi-scheduled instances, it will be very easy for you to add, remove, or update some of the instances without any downtime. And also, be able to run multi-schedulers also give you the ability to be able to scale out schedulers on the process level. Those are the motivations that we usually run multi-schedulers. So let's see how Kubernetes enables us to run multi-schedulers. These are about two features provided by Kubernetes. One is job dispatch. The second one is conflict detection. Let's say now you have a new scheduler. You want to run it along with the existing default scheduler process. If we really think about this, the first question will be, for a given pod, which scheduler instance should pick it up? As we just discussed, we usually develop different scheduler for different types of the workloads. So for a given pod, we do not want it to be picked up by random instance. We usually have a preference on which scheduler instance should schedule this pod. The way that Kubernetes solves this is pretty straightforward. First, now we have step 0. That's, first, we are assigning a schedule name to each scheduler instance. Currently, in the default scheduler, this is done by a command line parameter. So each scheduler instance will have a unique name in the system. And then, in the step 1, when a pod is submitted, user can set an annotation to specify the desired schedule name. And in step 3, when a scheduler picks up an unscheduled pod, it will check the annotation on that pod. If the annotation value does not match its own name, because it knows its own name, if it does not match, it simply drops this pod, because it knows that some other scheduler will schedule this pod eventually. And also, in the system, there is a predefined value for the default scheduler. So if the user does not specify this annotation, which is optional, the pods will be picked up by the default scheduler. Yes?
The name of the scheduler are persistent somewhere?
Name of scheduler? Yeah, this depends on the implementation of the scheduler. For the current default scheduler implementation, it's provided as a parameter during the command line parameter during the scheduler startup.
So if the user mistypes the name of the scheduler?
Yes, the scheduler instance. And this annotation is optional. If we do not specify, your pods will be picked up by the default scheduler instance.
If there is no scheduler, there is an error?
If there's no scheduler at all?
No, if the name of the scheduler is wrong.
Oh, if it's wrong, then the pod will remain in the pending status. Because we do not know if it's wrong or simply the scheduler instance has not been started. Yeah. The second feature that is provided by Kubernetes to support multi-scheduler is conflict detection. We can explain the problem with a very simple example. Let's say we have a very small Kubernetes cluster, which has only one node. And we have 2 scheduler instances. Now there are 2 pods are submitted to API server. And they are picked up by scheduler 1 and scheduler 2. Let's say both pods require 2 gigabytes of memory. And on the only slave load, we have 3 gigabytes of memory available. So what will happen is that scheduler 1 will think it's okay to put the P1 on the node because there are 3 gigabytes of memory available, while the pod only requires 2 gigabytes memory. The same thing will happen to scheduler 2, because scheduler 2 will see the exactly same thing. And now we can see what will happen if both pods are being launched on node 1. The resource will not be sufficient. This problem is a resource conflict caused by race condition. It can happen to other resource types like TCP pods or something else, not only CPU and memory. And this problem, we should be pretty familiar with it, right? It's something we always handle when we are doing some multi-threading programming. What Kubernetes does to solve this problem is simple and effective. In step 4, the last step when the Kubernetes tries to launch pods, now it will rerun all the predicates. So in this example, the first pod, P1, will be launched successfully. And then the available memory on that node will be updated to 1 gigabyte of memory because node 1 has already been launched. And then the Kubernetes continues to launch, tries to launch pod 2, and it will run all the predicates again. This time, the pod fits resource rule. Remember, we just discussed that rule. That rule will fail because the available resource on node 1 is not enough. So this is how the currently Kubernetes detects the possible conflict detection, the possible resource conflicts between different schedulers. And currently, it will not reschedule pod. It simply marked as a failure. So we have discussed how a single scheduler works in Kubernetes and why we would want to run multi-schedulers, and also how Kubernetes enables us to run multi-schedulers. In this part, I will talk about some work we did in our project trying to provide an enhanced support for multi-schedulers. As I mentioned earlier, all this work is a part of Huawei internal project named HOS, Huawei Orchestration and Scheduling System, HOS. So what exactly do we want to improve? First, in job dispatch area. In current Kubernetes solution, if there are several scheduler instances, the user needs to specify the name of the instance in pod annotation. Let's say sometimes we will run several instances of the same scheduler type. Let's say we run 3 instances, instance A, B, C. They are all same, have the same functionality. Actually, it will be difficult for a user to know which instance name it should set, because schedule A probably will be very busy, has a long scheduling queue, while scheduler B and C probably is idle. So if you specify schedule A in the annotation, your pod will have a very long scheduling latency. If you specify instance B and C, it will be scheduled very quickly. And this is hard for users to know which instance is the best one. So what we want to do here is first, we want to provide an instance level load balancing mechanism. So we will automatically help users select an instance. Second is about the dynamic scheduling policy. In current Kubernetes, as we mentioned, you can specify the scheduling policy in source codes or by command line parameter during scheduler startup. But after the scheduler is started, the supported policy is fixed, and it's only one policy. Here, we will support multiple policies, and the users can specify the scheduling policy it needs in the pod annotation. And our system will make sure the right instance, schedule instance, is selected for the pod with the scheduling policy support. In the conflict resolution area, currently the conflict detection, as mentioned, is implemented in Kubernetes. It's distributed, but there's a problem with scheduling latency. Because when the conflict is detected in Kubernetes, it usually is already about 2 seconds to 10 seconds after the scheduling time, depending on the cluster loading. This is not acceptable for some short jobs or streaming jobs, which have strict requirements on scheduling latency. So what we want to do here is to provide an early conflict detection mechanism. So any resource conflicts should be detected in the first place, and the pod should be rescheduled as soon as possible. This part of work is inspired by a paper from Google Omega, but we add lots of new features. Also, we want to provide flexible conflict criteria, so we can reduce the possibility of conflicts. And since there are many different schedulers, different workload types, we also want to provide a rich policy control on this conflict resolution. In the following slides, I will explain this work in detail. First, this diagram shows our enhanced job dispatch mechanism. If we compare this diagram to the previous diagram, we will see that first, in the step 0, we need to configure the scheduler type and instance names. Here, we run 4 instances for scheduler type 2 and 2 instances for scheduler type 1. In step 1, when user submit a pod, now they do not need to specify the instance name directly. They only need to specify the type. And we introduced a new module called scheduler controller. This controller is aware of all the running scheduler instances. It will assign a scheduler instance dynamically, trying to balance the node among these scheduler instances. And what it does is that it will update the existing scheduler name annotation. So the existing scheduler can still work in the same way. It only schedules the pods with its own name. But with this scheduler controller, we can make sure that if there are multi-instances of the same scheduler type, the queue is roughly same length, and the scheduling latency is roughly same. And we also support dynamic scheduler policy. User can specify the scheduling policy it wants, and the scheduler controller will make sure a right instance with that policy support being selected for that pod. This is our enhanced support for job dispatch. For conflict detection, the most important change is that we introduced a new module called conflict resolver in API server. This module will kick in when a binding request is submitted. A binding request, basically what a binding request does is writing the name of the node to the node name field. So how it works is like this. When a scheduler finds a best node for a pod, it will create a binding request. This binding request is submitted to API server, and then it's intercepted by our conflict resolver module. It will check if there are any resource conflicts based on the different criteria that are specified by the schedulers. If there is a conflict, it will return an error, and the scheduler is supposed to rerun the scheduling process immediately to find another node for that pod. In this way, we can capture any resource conflict in the first place and reschedule the pod, rather than writing the pod to the etcd and then waiting some time being picked up by Kubernetes, and the Kubernetes then spend some other time and then detect the conflicts. Now the conflict is detected immediately. And for the conflict criteria, we also provide a fine-grained model. Now there are 3 different conflict criteria in the system. Schedulers can choose the desired one based on its knowledge on the current pod or workloads. The first criteria is called a strong criteria, strong conflict criteria. It's based on the node resource versioning mechanism. We introduced a new versioning number for each node. The reason we introduce a new version number rather than reuse the existing resource version is because our new versioning number will only change when there are any resource changes, but the existing resource versioning will change every time when there is a heartbeat or something. So when a binding request is submitted, it will carry a previous version number that the scheduler saw last time. So the conflict resolver module will compare if the 2 numbers are same. If they are different, then a conflict is triggered. So basically, it means if there are any changes happen on this node after the scheduler gets the status last time, then it's a conflict. This mechanism is very, very strong. It makes sure the node status, resource status, is still exactly the same as the scheduler saw last time. But the possibility of conflict is high. The second conflict criteria is called weak criteria. It's not based on resource versioning. It's based on the node resource quantity. This is for some job types that do not require any special resource or any pods or something other resource. They only require some CPU and memory resource to run. So in order to reduce the possibility of the conflict, they can use this weak criteria. The conflict resolver will check, even if the version number has changed on the node, as long as the remaining CPU and memory resources are enough to run this pod, it will be regarded as a success case, not a conflict. So this provides a weak guarantee, but it reduces the possibility of conflicts. The third criteria is something between strong and weak. It's based on a Boolean expression. This expression can reference any node properties or pod properties. The conflict resolver will evaluate this expression. If the result is true, then it's okay. If it's false, then it's a conflict. So when scheduler submits a binding request, it can choose different criteria based on its knowledge on the pod and the workload. We also provide a rich policy control on conflict resolution. First is pod priority-based conflict resolution. Each pod is associated with a priority field, and accordingly, each binding request has a priority, which is the pod priority. We will first process binding requests that have a higher priority, because the earlier binding request is processed, the more possible it's being accepted. And now we are also trying to add a scheduler priority-based conflict resolution. This is because we find that some schedulers, because they have different implementation, the cost of rescheduling is more expensive than some simple schedulers. So it makes sense to give high priority to this kind of schedulers to avoid its rescheduling. And we support batch conflict resolution. This means that when a scheduler submits a binding request, it can submit multiple binding requests together. This probably is not very useful for the Kubernetes default scheduler because it schedules pods one by one. But for some schedulers that schedule pods in batch, this is pretty useful. It improves the performance. And furthermore, we provide group-based conflict resolution. This means, let me explain it with an example. Suppose a scheduler submits 10 binding requests together as a batch. Among these 10 binding requests, probably the first 3, the binding request 1, 2, 3, they have some affinity or anti-affinity constraints. So the scheduler will want to, these 3 requests succeed or fail together as an atomic unit, while the remaining 7 requests can succeed or fail independently. So it can specify different groups. In this way, we can provide the required semantics constraints, at the same time reduce the possibility of conflicts. All this work I described, the group-based conflict resolution and the third criteria hasn't been done. All the other things have been done. This is a picture shows all the current schedulers that run on top of our enhanced multi-scheduler framework. The first one is the Kubernetes native scheduler with some performance improvements. The second one is a scheduler called Firmament. It came from Cambridge University from a research project, and it was originally written in C++. we have some collaboration with also, and we changed the implementing language from C++ to Go and adapted it to Kubernetes. I know that CoreOS is also doing the similar thing, and they demoed some of their work in one of the scheduling SIG meeting. The third scheduler is called a Tasia scheduler. It's from a paper from Stanford University. The idea is that for some batch jobs, short jobs, we do not need to evaluate all the nodes in the cluster, assuming the cluster is very large. We just evaluate some sampling nodes based on the cluster loading status. And we also modified the Mesos master and the Young resource manager so we can support existing Mesos schedulers and the Young schedulers. They will get the available nodes resource information from us, and then submit their scheduling requests in the same way to conflict resolver, just like any other scheduler in the system. These are the supported schedule now. The last slide is about the multi-schedulers in Mesos. As I just mentioned, during the house project, we also evaluate how multi-schedulers are supported in Mesos. It's pretty interesting to see how it's done in a totally different architecture. So I'd like to share our understanding here too. Of course, there are many differences between Kubernetes and Mesos. In terms of scheduling or multi-schedulers, there are two differences that we need to pay attention to. First, we know that the Mesos master itself doesn't do scheduling. All the scheduling are done by different schedulers in different frameworks. This diagram shows two application frameworks running on top of Mesos. And each scheduler has its own task queue that do not share a global queue. When a user is trying to submit a task to Mesos, it's talking to the corresponding frameworks rather than Mesos master, because they do not share a global task queue. So there is no need to have an annotation or something to do the job dispatch. They are naturally dispatched. Second, for the resource conflicts caused by race condition. In Mesos, each scheduler is not able to see the global state of all the available nodes. Instead, it can only see the nodes or resources that are being sent by Mesos master to it, which is called a resource offer. In this example, the Mesos master is sending a resource offer to scheduler 1. And the scheduler 1 decides to put 2 tasks from its task queue on this piece of resource. The important thing is that at one time, one resource offer is only sent to one scheduler. So the scheduler 1 doesn't need to worry about any resource conflicts caused by the risk condition. So we can see that in Mesos, we do not have the problem of job dispatch and the conflict caused by risk condition. But does this mean it's a better architecture or perfect architecture? It's not. It's basically a pessimistic style, concurrency control style, while Kubernetes is an optimistic concurrency control style. The problem with this pessimistic control style is that concurrency control style is, first, the scheduling quality is not good in some case, because the scheduler simply cannot see their beta nodes in the cluster. It can only see a part of the nodes. So sometimes the scheduling quality gets hurt. Second, the resource, because it's a kind of pessimistic locked concurrency control, the resource utilization is not very, very high. For some large tasks, they probably will need to wait a long time before the scheduler can get a large enough resource offer to run this task. So naturally, this scheduler tend to cache resource offers, even they do not need to use it right now. This causes the resource utilization not high. In Mesos community, now there is an ongoing effort called optimistic offers, which try to address these problems by providing resource offers to multiple schedulers at the same time. But this will cause conflict as well. The last page is a summary of this different 3 different systems. We can see that you can treat a host as an enhanced Kubernetes. On concurrency control, both Kubernetes and host are optimistic, while Mesos is pessimistic. Here, we do not include the ongoing optimistic offer improvement for Mesos. For scheduled resource view, Kubernetes and host, they are based on shared global state. So our scheduler can see all the available nodes resources in the cluster, while Mesos master can, Mesos scheduler can only see partial nodes. For job dispatch, Kubernetes now supports multi-type. We support multi-type, and we also added a multi-instance and dynamic policy support. For conflict detection, Kubernetes is a kind of late detection mechanism, and we are based on early detection mechanism. And for conflict model, we are fine-grained the model. We include different criteria and also different policy controls. These are some reference and further readings if you are interested in this field. We are trying to finish some of the work. We have finished most of the work, but there are still some of them not finished. We are trying to finish all of them, stabilize them, and open source the multi-schedule framework. This is pretty much what I have today. Thank you. Any question? Sure. Oh, sorry. Which one?
Just to the further reading.
Oh, further reading. Okay. What's your question?
Sure. So part of the work you're doing is to improve performance and faster scheduling, right?
Yeah.
But
And also more flexibility, like the policy control.
Yes. Under heavy load and heavy conflict, there's no proof that you're improving performance. You might be reducing performance. A lot of conflicts between schedulers and rescheduling.
Yeah.
Maybe a single scheduler is faster.
Yes.
That's why distributed systems like etcd or PaaS, you have a leader.
Yes. This is possible because even within one scheduled process, you can run multi-threads, right? This will cause conflicts too. I just mentioned that in our system, we run the Kubernetes default scheduler with some performance improvements. What we did is that we partitioned the nodes to reduce the conflicts or possibilities. And also in the slide about the benefits of running multi-schedulers, I mentioned that we have the ability to scale out. But I didn't say it definitely will have a better performance than single scheduler. It all depends on your scheduling algorithm.
And you talked about priority-based conflict resolution.
Yes.
When you introduce priority, you risk starvation for the pod.
Yes.
Low priority.
Yes. If it exceeds a certain amount of time, we will return fail directly. Yes. Sorry, do you need this? No.
Sorry.
Oh? Maybe it's...
Hello?
Okay. I can hear the question now.
The question is about gang scheduling in the optimistic case.
Yeah.
So you mentioned that you can hoard offers in the pessimistic case, but how would you schedule a constellation of containers when you can get conflicts and whatnot? So
Sorry, I didn't get the question.
it's like about the gang scheduling pattern.
The game scheduler?
Yeah. So if you need to schedule
What's your-
n things,
Sorry, which game scheduler?
I don't know how else to explain it. So like in HPC,
Yes.
you need 10 things to all come up at once,
Yes.
and 9 won't do. You need all 10.
Oh, yes.
Yeah. So you can do that in the pessimistic case, but how would you do it in the optimistic?
So the question is, my understanding is that you want to try to allocate the 10 containers as a group, right?
Yeah. Exactly.
In the pessimistic case, it's actually still same. In our model, the scheduler will submit these 10 requests together, and the conflict resolver will evaluate if all these 10 requests can be fulfilled at the same time. If not, simply return false. The scheduler needs to pick another 10 candidates to request.
So you can submit the custom,
yes.
custom
Constraints. That's,
Exactly.
it's kind of transactional. So I have the last example is that I submitted 10 binding requests, but 3 of them are in a group or transaction. These 3 the conflict resolver will make sure they either succeed or fail together. They will not be handled independently.
Do you have any data on, random fit versus the default schedule versus your improved one?
Oh,
Let's say, you're trying to solve the issue of conflict resolution.
yes.
You'll have to have some data saying conflicts were a problem before.
Yes.
So too many reschedules are happening or whatever.
Yeah.
Do you have data for that?
Because we are just finishing the data, we are still running some functionality tests. We do not have the exact data for that part. But in our implementation, we didn't change the possibility of conflicts, because in the original model, it's kind of a strong conflict criteria. We are trying to provide more options to reduce these conflict possibilities. So we will not increase the conflict possibilities. And also for the conflict resolution itself, it's stateless in API server. So if there are too many requests, we can scale out with the current API server HA mechanism. We run multiple API servers. That's supported. Okay, so that's all. Thank you.